Presenting our progress report video for everything we've been doing throughout the semester. My name is Simon. I'm an electrical engineer. John is our other electrical engineer. Kevin's our computer engineer. And Derreck is our mechanical engineer. And we're working on our project, which is ice detection for airplanes. So, with that being said, let's just jump into what we're doing. So the main issue with airplanes is that when planes are flying at high altitudes, it tends to get very cold and ice starts to form on the wing of the plane and the body of the plane. And this is an issue for a multitude of reasons, but it just makes it harder for the pilot to control the plane. And so pilots do have ways of de-icing the plane, but the issue is that they don't have a way of detecting or knowing when ice is starting to accumulate because, all their attention is on all the other things that they're doing, and it can be hard to look to see whether ice is forming, and current solutions are not that great too. So our project mainly focuses on detecting the ice automatically before it becomes an issue, which just it loosens the burden that would be on the pilot so that they can focus on other things. So the main way we're planning to use this is by utilizing piezo technology. The reason why we're doing it is because our stakeholder suggested that we use that. And in addition to that, piezos also are very good for detecting ice because piezos vibrate at a certain resonant frequency. And when you put ice on it, the resonance changes due to the ice being on it, the load. And so if we can measure the frequency, or if we know the resonance frequency and we can measure it, we can see if there's any fluctuations or differences of the frequency, and that tells us that there's ice on our plane. So that's basically the main idea for our project. So initially, we wanted to find the resonance frequency of the piezos that we had just to find out what the baseline was for where the piezo should be. So we did this by using Agilent and just putting piezo into a breadboard. And we flicked the piezo to give it a little spike, and we captured that spike in Agilent, as you can see in the slides. It has like a bunch of peaks like going down because it wobbles for a little bit and then it stops, and that's represented by the peaks just going down and down until it's back to where it was. And so we measured the period between the peaks to see what our frequency was, because for frequency, how you find that is just 1 over period. So when we found the period, which was around 8.75 milliseconds, we used that to get a frequency of 114 hertz. And this frequency, we verified that it worked by putting in the frequency in Agilent, and we put it back into the piezo, and we were also measuring the piezo to see whether the waveform would jump up, because if you put the resonance frequency into like an already existing wave, it's the resonance if it makes the wave go up, right? So when we put it in, we were able to get it to work with a resonance of around 115, which is really close to what we had. So we knew we were on the right track for that. But an issue we ran into is that the piezos that we were using had a really high resistance. The resistance was so high that when I tried to measure it, it literally just told me overload, which is not good because we moved from trying to measure the voltage amplitude we moved from doing it on the piezo itself to doing it through a resistor instead. And the resistor value we chose was around 325 ohms, but because the piezo resistance was so high, it just caused a lot of issues with measuring it because that one resistance was way too high to be useful. So we ended up having to actually use another piezo that just worked better for us because this one wasn't really giving us the stuff that we wanted.
When we were first starting the project, the first thing that we looked at was doing an FEA analysis of an aluminum ruler, which takes the wing and simplifies it because they could both be treated as cantilever beams. However, talking with our stakeholder and our advisor, they told us it'd be better to find the resonance frequency of the piezo itself instead. And so we modeled the piezo, which was a thin film piezo at the time, and calculated the resonance frequency, which in this case was 125 hertz, which was what the software told us. But in actuality, it was about 115 hertz, which is very close, but not precise, but gives us a general idea of where we could find the resonance frequencies of these piezo sensors. And taking a look with the new piezo sensors that we got, I was able to model the sensor itself using diagrams that the manufacturer had given us, and we were able to calculate a resonance frequency that is around the same frequency that's on the spec sheet that was also provided by the manufacturer as well. And so, taking these different modes, we could see around where the resonance frequencies of the new piezo sensor is, and it falls along the line of where the spec sheet is, but the spec sheet, the problem with it is that it doesn't give exactly the number. It gives you a value and then a tolerance of about a couple hundred hertz, so you kind of have to like dig through it, and this helps us identify the exact frequency. And so using this, we were able to identify around where we can get the peak resonance to get the peak output voltage of the piezo sensor. And so one of the other things we look at is being able to suspend the plate and isolate it from any other damping sources, so a table or anything that can latch onto it that can also damp its frequency. And so this is two models that were designed, and one of them was suspending it laterally on a 3D printed plate with a hole in the middle so that it isolates itself. And the second design was suspending it from an overhang where it'll kind of dangle down from the top of it, which is the preferred method because it allows for more room for it to be even more isolated than design one, but that'll come at a later point in time. And so taking the SolidWorks model where we could see how this would work for our first design, which we're probably going to plan on testing as soon as this gets done. And we could see that you have the big hole in the middle that allows for the plate to be suspended in the air, and you have the little the little extrusions that are coming out from the corners, which we'll use to wrap string around it, and then drilling some holes in the plate, we can suspend it and then use the piezo sensors in isolation with the plate so that there's nothing affecting it from the any external sources.
Alright. Now, as to what I've started or began with was I tried to make a nice simple LCD display just show me anything on the screen. I just started programming LCD screen so I can eventually connect it to piezo. The initial piezo we got did have struggle getting the original resonance, so it did take me quite a while before I was able to do anything with it. again, we ended up switching to the new piezo. This is the spec sheet for it that was graciously we found upon buying the new one. We were able to find various amounts of information about it. Some of it actually has quite accurate information and also has some varying information. As Derreck was saying before, we were able to find some resonance frequency, but the piezos all in our that we all obtained were all varying. So not all of them had a 4.6 kilohertz range of resonance, as well as their impedance. Their impedance usually stays around that 300 range, which is wonderful. Using this new piezo, we were able to make more measurements. This was my failed attempt at trying to measure the frequency of the piezo through an Arduino. I try to use a fast Fourier transform to use UART to send it to the serial communicator, so that way I have a nice clean plot of it. Initially, it wasn't really giving me much. It started off well, giving me a nice 0 as a base when I didn't do anything to it. And then eventually, once I started hitting it, it started giving me spewing out ASCII. And I wasn't able to resolve this. So I ended up removing to something else. So these are plots that we use using our Agilent oscilloscope. And these plots weren't the greatest. This is probably one of our best graphs showcasing the single piezo mounted, as we were able to get some sort of peak from it. But we consider this overall to be a failure, as to when we compare it to our other graphs. The graphs have some points that you're able to see where the resonance peak would be, but it's not really clear like the first one. And as we can move on, it shows more and more like it's very not consistent, and we couldn't use this as our basis. As well, since I moved away from using that frequency detector for the time being, I decided to make a different sort of sensor. Since we have to be able to detect ice, I started making a pressure sensor, so that way whenever a new mass is added to the plate, it detects that there's something there and it lights up the LED. And it's going to basically from there then go into a trigger where it's going to add warnings, and depending on what type of mass is being added.
So to get an idea of what was going on
John?
within the new piezo, we decided to run a few experiments just to see its reaction at different frequencies. So the first experiment was comparing its frequency of one piezo when it was attached to an aluminum plate, and its reaction to the same frequencies when it was just floating in free space, allowed to vibrate. So this piezo didn't work at the small voltages that Agilent can output. Agilent can put out like 1 volt or so. 1-2 volts, something very small. So we used an op amp and we kind of biased it at around 16, something like that, volts, 16 to 20 volts. But the output voltage was around 12 to 13. So that was what was going into the piezo. And we observed these trends, right? So we sine swept it first to see if there was anything to even be searching for. And when we saw that there was, we manually started at 50 hertz and went all the way up to 10,000 hertz to observe the trends. And if we look at the mounted graph here, see that the peak happens at around 3,000 hertz. And it's just gradually going up until that point, and then it just starts to go down. So that's kind of the big hitter here. For the not mounted graph, so the first not mounted graph, you see that it's a bit sporadic. The data is just everywhere. Although it kind of does land somewhere between like the 1500 and 3000 range is like the hitter, but that's not really concrete. And again, for the second not mounted graph, it's a little bit more linear, but it's kind of just a flat line. It's where the average is. So the idea was, well, what if we decided to have a backup piezo? Because if one piezo is acting as both the conductor and the generator that the oscilloscope is measuring, maybe it's just the piezo itself is being overpowered. It can't handle it, which is why we see this single just flat line from when it was in free space. So in this slide, where the two pieces are stuck together, they're quite literally taped and gorilla glued together, and they were attached to separate breadboards. So one of them was attached to the whole op-amp circuit to get the 12, 13, 14 volts, whatever it was. And the other side was attached to just a random breadboard. We put the oscilloscope across it. So when they were mounted, we saw a much, not nicer, because it's still very sporadic in certain regions, such as the 1 to 2000 region, but there was just a very clear peak, right, around 3200 hertz. Right, it peaked all the way up at 32-ish millivolts, which is really high considering it was averaging around 12.7 or so millivolts for everything else. So that's pretty much where our resonance is. For when they were stuck together, we see a very unusual trend, right? We have multiple peaks, and each peak kind of goes down, but the peaks are also very close to each other, right? We got the first peak at around 1100, second peak at around 1900, and then the third peak is like at around 3200. The 3200 matches up nicely with what we were seeing before. These other two peaks are very strange. We ran the test over and over, and we kept getting that peak. So what we're assuming is possibly something to do with harmonics. We got to research more on this. We're not really entirely sure. But again, the big focus was for its reaction to when it was mounted. Because when it's mounted, that's what the prototype is going to be like. And we can use this very big change to create the sensor that Kevin was talking about.